Hi, in this video, I will be showing you problem number 1 of chapter 16, section 9. Verify that the divergence theorem is true for the vector field F on the region A, where the vector field f of x, y, z equal to 3xi plus xyj plus 2xzk. E is the cube bounded by the planes x equal to 0, x equal to 1, y equal to 0, y equal to 1, and z equal to 0 and z equal to 1. So we are asked to use divergence theorem to find out, we are asked to verify the divergence theorem. So let's see what divergence theorem is. Here also you are given E is the cube bounded by the planes x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0 and z equal to 1. What is divergence theorem? State the divergence theorem. Let E be a simple solid region and S be the boundary surface of E given with positive outward orientation. Let F be a vector field whose component functions have continuous partial derivatives on an open region that contains E. Then double integral over S f dot ds equal to triple integral over E div f or divergence f dv. Here also you notice that simple solid regions are regions bounded by closed surfaces such as ellipsoids or rectangular boxes. This theorem actually states that the total divergence of a vector field in a solid region E is equal to the total flow across the boundary surface S. So the flux integral is actually equal to the total divergence of the vector field in a solid region E. This theorem also shows the relationship between a triple integral over a solid region and a surface integral over a surface. To show that double integral over S f dot ds equal to triple integral over E div f dv, we will go one side at a time. So consider the right hand side, which is triple integral over E div f dv. So we have to compute the divergence of f. So f is given by 3xi plus xyj plus 2xzk. So div f is dou by dou x of 3x plus dou by dou y of xy plus dou by dou z of 2xz. Dou by dou z, I mean partial derivative with respect to z. So this gives 3 plus x plus 2x, which is equal to 3 plus 3x. We'll call it step number 2. Now triple integral over E div f dv is integral 0 to 1, integral 0 to 1, integral 0 to 1. So those are the limits for x, y and z, so which is inside the integrand it is div f, which is 3x plus 3 dx dy dz. So it is integral 0 to 1, integral 0 to 1, 3x plus 3x square over 2 by integrating that with respect to x, 0 to 1, and then dy dz. If you compute this integral, it's going to give us the right hand side, which is in triple integral over E div f dv is nine halves. So if we compute this triple integral, it will turn out to be 9/2. So keep in mind this is only definite integral. All the limits are 0 through 1. So first you integrate it with respect to x, and then that turns out to be 9/2. Then it is double integral 0 to 1, 0 to 1 dy dz, which is just the area of the square, which is equal to 1. So it is 9/2. So we got one side of the theorem. Now we have to do the double integral over s f dot ds, which is the left hand side of the theorem, which we have to verify. To compute the left hand side, double integral over s f dot ds, we'll consider the surface. We'll sketch the diagram of the surface here, which is the cube of each side being equal to 1. So we have xyz axis. Then each side is of length 1. So draw a cube where each side is of measure 1 unit. We shall compute the integral on these 6 faces. Double integral over s f dot ds on each face of the cube. So double integral over s f dot ds equal to double integral over s1 plus double integral over s2 and so on up to double integral over s6. There are 6 faces. For each one of them we have to compute the integral and add all of them in this step. Where s1 will correspond to x equal to 1 side, s2 will correspond to y equal to 1 side, s3 will correspond to z equal to 1 side, s4 will correspond to x equal to 0, s5 would correspond to y equal to 0, s6 will correspond to z equal to 0. So we've got 2 steps here. So double integral over s1 f dot ds. In order to compute that, we need to write that as double integral f dot n ds. So we have to find out the unit normal vector to that side, s1. So this s1 is shaded yellow in the figure. So the unit outward normal is actually I. On s1, x equal to 1, f equal to, so we can substitute x equal to 1 in the vector field f, which is 3i plus yj plus 2zk. Then unit normal vector is actually n, which is equal to I. So if we do f dot n, so double integral over s1 f dot ds, which is double integral over s1 f dot n ds on s1 n equal to I. So if we multiply f and n, dot multiply f and n, we'll get 3i plus yj plus 2zk dot I, which will be just 3. So double integral over s1 f dot ds, double integral, which is double integral over s1 3 ds, which is 3 times double integral dy dz, which is the area of that side, which is equal to 1. Area of the side where x equal to 1, which is equal to the square is of length 1, each side is 1, so area of that square is 1. So it is also integral 0 to 1 integral 0 to 1 dy dz, which is equal to 3 because of this 3 outside. And this value is equal to 1. Now similarly we have to find out the integral over s2, s3 and so on. So we'll call that one as step 1. On s2, y equal to 1, if you compute f by substituting y equal to 1, we get f equal to 3xi plus xj plus 2xz k, n for that side with y equal to 1. If you look at this side, so the S2 is shaded in green. For that side, unit normal which is outward positive normal is going to be in the direction of y, which is j. So n equal to j for that side, so double integral over S2 f ds would be double integral over S2 f dot n ds. So if you dot multiply with the j, f and n, you're going to get just x here for the integrand. So it is x ds, 0, integral 0 to 1, 0 to 1. This corresponds to the side, the face of the cube y equal to 1, corresponding to the face which corresponds to y equal to 1. So if you integrate this, it is integral 0 to 1, integral 0 to 1 x dx dz, so which is 1/2. So we'll call it step 2. Then on S3, z is equal to 1. So z equal to 1 on S3. So if you substitute that z equal to 1 into f, we get 3xi plus xyj plus 2xk. And the unit normal vector for that face is going to be upward, positive normal is going to be k. So if you do f dot n here, and double integral over S3 f dot ds is double integral over S3 f dot n ds, which will turn out to be 2x ds. This side corresponds to the plane parallel to xy plane. So ds is actually dx dy. So it is integral 0 to 1, integral 0 to 1, 2x dx dy. If you compute this integral, that will turn out to be 1. We'll call it step 3. So on S4, the side corresponding to S4 is x equal to 0, which is pretty much the yz plane or x equal to 0 plane. Here if you compute double integral over S4 f dot ds, double integral over S4 f dot n ds, but f itself is 0 because x equal to 0. So this value is going to be just 0. On S5, y equal to 0, we'll substitute that into f. So that will become 3xi plus 2xk. Then unit outward normal is going to be negative j here. So f dot n pretty much is 0. So because of this, the integral value over S5 is going to be 0. The last phase is going to be S6. On S6, z equal to 0. So if you substitute z equal to 0 into f, this will become 3xi plus xyj plus 0k, and n is negative k, that is the outward normal. So if you dot product f and n, it will become 0. So double integral over S6, 0 ds, which will be 0 as well. So we notice now we are going to find out double integral over S by adding all the integrals on each one of these 6 faces. So we get double integral over S f dot ds, which is double integral over S1 plus double integral over S2 up to double integral over S6. So from 1, 2, 3, 4, 5, and 6, we substitute the values that we got, which is 3 plus 1 half plus 1 plus 0 plus 0 plus 0, which is 9 halves. So earlier from the first method, we actually got this value to be 9 by 2 by applying the right hand side of the divergence theorem. Now it is double integral over s f dot ds equal to 9 halves. So on both sides we arrive at the same value. Thus the divergence theorem gets proved. So a double integral over s f dot ds equal to triple integral over e div f dv. So we have proved both sides are equal to 9 halves. So proving divergence theorems may be a little time consuming work, but if you are applying divergence theorem to find out one of the sides, then the problem becomes much easier. Hope this video helps. Watch my next video where we use divergence theorem to arrive at the surface integral.